Today's lesson is dedicated to the study of fresh water as a limited resource. Studying the water cycle, we tend to believe that water is an unlimited resource, and while it is true that the amount of water on the planet is constant, it is not always found in an adequate and available form to be used by living beings and more specifically by humans. Let's start by taking a closer look at the distribution of water on the planet. Seen from space, the color of our planet is mainly blue. If you look at the graph, seas and oceans cover almost 97.5% of the Earth's surface. This water is salty, so it can't be used by living things. Inland waters are found on the continents. They are freshwater masses with a low concentration of mineral salts. And only 0.4% of fresh water is available as surface and atmospheric water. They are the main sources of drinking water for living beings. We now move on the use of water by human beings. Water used by humans is classified into non-consumptive and consumptive use. Non-consumptive use includes those uses that allow water to be returned to the hydrological cycle after its use. Examples include recreational activities such as swimming pools and aquatic parks, transport, and hydropower generation. In consumptive use, water cannot be returned and treated to the hydrological cycle once it has been used, as its quality has been altered. Focusing on consumptive use, we must highlight industrial use, which accounts for 15% of human activities that use fresh water, and which involves using water for the manufacturing of products or energy production. For example, to manufacture a piece of paper, more than a liter of water is needed. In addition, there is domestic and urban use, which accounts for 25% of human activities that use fresh water and which is destined for maintaining green areas, cleaner streets and homes, personal hygiene, drinking, cooking. And finally, agricultural and livestock use, which, as we can see, accounts for 60% of human activities that use fresh water and which is destined for irrigation of crops and feeding animals. Thus, to obtain a kilo of potatoes, 500 liters of water is needed. For 1 kilo of chicken, 3,500 liters, and for 1 kilo of veal, 15,000 liters. Let us stop for a moment to understand where the water that comes out of the tap in our homes comes from. Drinking water is the water that human beings can safely drink without damaging their health. It is characterized by the fact that it is odorless, colorless, with pleasant taste, and right quantity of gases and mineral salt, pathogen-free, and without harmful chemical substances. This water is produced in drinking water treatment plants. Drinking water treatment is a set of physical and chemical processes that turn natural water into drinking water. Let's see in the video what the process consists of.
Access to fresh water is one of the largest drivers of creating a modern society. But what allows everyone access to seemingly endless supplies of potable water? It depends on where you live, but chances are behind your tap, there's a municipal water treatment plant. There are two main types of water treatment plants, drinking water or wastewater plants. We'll be focusing in on drinking water plants here, but if you'd like to learn about how wastewater is treated, you can watch the video linked in the upper right here. The question still remains, how exactly does one treatment plant take dirty river water or well water and turn it into water that is safe to drink? It involves a lot of processing, using chemicals, filters, and removing all of the toxins and hazards from a given source. The entire process starts with something called coagulation and flocculation. All drinking water has to come from somewhere, usually being freshwater lakes, rivers, wells, or streams. In these water sources, there's going to be some amount of sediment as well as organic materials in the water. These particles of sand, bacteria, dirt, wood, etc., they all have to be removed before the water can be sent out to city residents. To do this, chemicals called coagulants are added to the water. These chemicals, such as aluminum sulfate or ferric chloride, work to help the particles in the water congeal together. Essentially, these chemicals have the opposite charges of suspended solids, like clays or silts. When combined, the charges of the particles are neutralized, allowing for them to stick together. Coagulants are often added to the water right at the inlet of a drinking water plant, where the water then goes into mixing basins called flocculation basins. In these basins, the solution of water and coagulant will slowly be mixed together to form what are called floc particles. After mixing for a set amount of time determined by water quality in the flocculation basins, the water is moved to sedimentation basins. It's in these holding tanks where the water sits for the floc particles to begin settling out at a faster and faster rate, which is the intended goal of this process. By simply adding and mixing these chemicals into the water and letting that water sit, a large portion of the sediment will settle out to the bottom as sludge, which can be taken away to a landfill or holding facility. The floc particles are ultimately removed from the bottom of basins, and the clean water, being the cleanest at the top due to the settling particles, flows over weirs to the next stage in the process. In some plants, engineers actually use dissolved air flotation tanks in place of sedimentation basins. In these cases, air is pumped into the bottom of the tanks, creating a cascade of tiny bubbles. As these bubbles float to the surface, they take floc particles with them, forming a film of floc on the surface of the tanks. Then, a sweeper arm pushes the floc into a collection basin where it's taken to a handling facility. In dissolved air flotation tanks, the clean water is taken from the bottom, where the least amount of floc is. When it comes to designing wastewater treatment plants, engineers will vary techniques based on the water source and how they want their final water to taste, feel, or otherwise be treated. The only regulation is the quality of water being pumped to the city, and in most cases, it doesn't matter how plants get the water to that point, which allows civil engineers a lot of creative freedom in the process. After the majority of solids are removed from the water during coagulation and flocculation, followed by sedimentation, the water flows over weirs to the next step, filtration. The water at this point will start looking clear, but there will still be bacteria and very small suspended solids in the mix. The filtration process will seek to remove the remainder of the suspended solids and bacteria to further bring the water up to snuff. Nearly every potable water treatment plant will use a sand filter for this process. Even in plants where engineers may not think it's needed, often sand filters will be added simply for extra measures to ensure clean water at the end. Sand filters are exactly what they sound like, a basin of fine to coarse sand that filters water. It would theoretically be possible to treat drinking water with only sand filters, but that would result in frequently clogged sand filters, resulting in lower efficiency and more cleaning time. These sand filters can be set up in essentially two different ways. Either the water flows from the bottom and exits the top, or the water flows from the top and exits the bottom. Each layout presents its own set of unique problems, but the most common technique is actually for the water to flow from the bottom to the top. Sand filters aren't highly technical. Water just passes through them and particles get caught as they run out of space to flow through. However, while not highly technical, sand filters are highly efficient. Water flowing out of sand filters will need to have a clarity of around less than 0.3 nephelometric turbidity units, or NTU. Try saying that 3 times fast, or whatever local code is used for water clarity. This measurement is essentially just a way to determine the number of particles still remaining in the water, or turbidity. Many treatment plants will also pass water through activated carbon basins, which you can essentially think of as giant Brita filter tanks. Activated carbon particles have hundreds of tiny pores on them that help remove the tiniest of sediment and bacteria. This process isn't wholly necessary, but it helps improve taste and odor odor, often a desired trait for city residents. At this point, the water should be mostly crystal clear, but there still remains some residual bacteria. That leads us to the next step: disinfection. There are three main ways of disinfection in the water treatment process, which can be used individually or in combination with one another, depending upon design. First, chlorine or chloramine treatment. There's ozone treatment, and finally, ultraviolet radiation treatment. In the US, the main method of disinfection is by adding chloramines, or chlorine-based compounds. These compounds, such as chlorine dioxide or monochloramine, work to kill microorganisms. One downside to this process, though, is that these chemicals can react with other organic material in the water to create disinfection byproducts. These disinfection byproducts are harmful to human health and have to be prevented or mitigated. This extraneous reaction with other organic material is also why chlorine disinfection must come at the end of the treatment process. If added at the beginning, an abundance of disinfection byproducts would be created, causing a plethora of issues for the engineers and plant operators. Even with all of this, chlorine is used mainly because of how it kills pathogens. It not only kills any pathogens in the water at the plant, but residual chlorine levels also remain in the tap water, killing any contaminants that might get introduced after leaving the plant. Most cities or states will have maximum or minimum chlorine levels in the treated water in order to keep both the water treated and city residents safe. The other most common method of treatment is ultraviolet radiation. In this process, UV light is shined through the water, which scrambles any bacteria's DNA. This doesn't kill the bacteria, but it makes it impossible for them to reproduce, thus making them harmless. The main downside to this disinfection process is that it isn't residual like the chlorine, meaning that any bacteria introduced to the water after this process can't be treated. Finally, we're left with ozone treatment. This process involves adding ozone, O3, to the water. Called ozonation, the ozone kills the bacteria in the water as well as improving the taste and odor. In most cases, this treatment process also requires that a chemical be used to remove any ozone at the end, such as sodium bisulfate, as not to cause any harmful effects to the city's population or anyone who might drink the water. After the water is treated in any one of these three disinfection processes, it's ready to be pumped into a city's pipe network for delivery to your tap. The water flowing out of a plant is tested for various levels of chemicals, particles, and other qualities, all outlined in a plant's permit. This permit, set by the governing agency, regulates water quality and holds the treatment plant accountable in the treatment process. At this point, all the water is fit for human consumption per the permit, and the treatment plant is tasked with keeping it flowing through the pipes in your city. Constant pressures of 40 psi must be kept at the outlets of the water in the system so that in areas of high elevation in the pipe network, the water retains residual pressure. 1 foot in water elevation is directly correlated to an increase or decrease of 0.433 psi. So as water is pumped throughout the city, its pressure at any given point of differing elevation fluctuates. Positive pressure always has to be achieved as to not let any external water in the ground flow through pipe cracks or joints. This would contaminate the entire system and is one reason why you might experience a boil water notice. Essentially, that means engineers have reason to believe that somewhere in that city's pipe network dropped below the required PSI and water or contaminants might have infiltrated the system. Massive pumps at the treatment plant supply pressure to the system through constant operation. Some of this pressure can be stored as elevation in water towers, which can give pumps a backup in emergencies or fire flows. In a lot of cases, water towers allow the pumps at the treatment plant to run at a constant rate, which increases efficiency and removes downtime problems. This combination of pumps and water towers allows your tap to remain flowing and otherwise allows you to live in the comfort of your own home. Civil engineers and treatment plant operators work around the clock to provide clean water through water treatment plants. At this point, we've taken a look at the most common potable water treatment techniques, but there are tens to hundreds of other deviations we haven't discussed. This draws back to one of the coolest things about water treatment plant design. You're able to use any number of creative solutions to clean the water, and as long as it comes out clean, you've done your job well. Don't forget about the thankless job of being a water treatment plant operator, though. These men and women work around the clock to keep treatment plants running 24/7 so you can always have fresh water. A lot of time, money, and effort goes into making sure that you can have that nice glass of water on demand.
It is very important not to confuse drinking water treatment with purification. As we have already mentioned, the consumptive use of water alters its quality and therefore it must be treated before being returned to nature. This process is carried out in sewage treatment plants. Contaminated water must be treated to remove physical, chemical, and biological contaminants, which are then dumped into the environment. Let's watch the process in this video.
It's a topic we'd rather not think about. Where does last night's dinner go when we flush it down the drain? While you may already be grossed out just thinking about it, this question leads way to a significant subset of civil engineering and a massive amount of public funding. Just like all dogs go to heaven, all drains in a city lead to a wastewater treatment plant where that wastewater gets turned back into water that we can drink. Now, you may be thinking that you'd rather just let bygones be bygones and not think about this nasty part of real life. But here's the thing. Chances are you've drunk water that was waste at some point, so you might want to take some time to understand this engineering process that makes dirty water clean. Here's where it starts. The toilet. Once you're done doing your business and flush that magical handle, your waste ends up at the inlet of one pretty interesting place, a wastewater treatment plant. Why is this place so interesting? Because it takes arguably one of the most disgusting substances in the world and turns it back into something that is essential to all life. Flushing just your toilet at halftime may not seem like a big deal, but when you couple it with thousands, if not millions, of others doing the same, it can result in some pretty high sewage flow rates. New York City has an array of 14 wastewater treatment plants that handle a combined 1.3 billion gallons of wastewater daily. That's enough wastewater to fill the Dead Sea with pure sewage in just 8 years. And that's just New York City. There are an estimated 14,748 treatment plants in the U.S. alone that 76% of the USA's population relies on, according to the American Society of Civil Engineers. Understanding wastewater is crucial to understanding the critical infrastructure needed to support modern life. That brings us to the first step of the process that handles larger items in sewage, things like flushable wipes, 2x4s, toys, or even guns. You name it, and it's probably been caught in a bar screen. Bar screens are exactly what you would think. They are large vertical bars that stand at the inlet of nearly every wastewater treatment plant, designed to stop larger items from getting to the plant and hurting machinery like pumps. This first process where bar screens are used is commonly referred to as pre-treatment. The sole intention of pre-treatment is to remove the outliers in the sewage and make the whole mixture a little more homogeneous, or slightly less chunky. Bar screens are typically mechanically raked at certain intervals, depending upon the flow rates of the water treatment plant, although some older plants will still have more manual removal processes. Whatever is removed from the bar screens is then sent off to your average landfill or solid waste handling facility. Or, in the case of unusual items, such as guns, they're sent off to the evidence locker in a police station to be investigated. Next up is the grit chamber. Grit chambers are the next steps in the pre-treatment process following bar screens. Since these bars don't catch everything, larger particles called grit still need to be removed from the sewage as it is made even more homogeneous. As the sewage flows into the grit chamber, the velocity of the rather viscous sewage is adjusted to allow for particles of sand and rock to settle out. This is needed because these particles can't be removed using chemicals, and they could potentially clog or destroy pumps later on in the process. There are 3 types of these chambers: horizontal grit chambers, aerated grit chambers, and vortex grit chambers, which all accomplish the same task using slightly different methods. Following the grit chambers, the sewage will move on to the primary treatment process, which starts with a large basin called a primary clarifier. Primary clarifiers and clarifiers in general function on the principle of settling velocity. This term can be defined simply as the speed at which a particle settles. For wastewater being pumped into clarifiers, it's important that the flow rate of the water being pumped in doesn't exceed the settling velocity of the particles trying to be removed. In order to accomplish this, engineers will vary the size and number of primary clarifiers in accordance with a plant's permitted sewage flow rate. This ensures that at varying flow levels, solids can settle out of primary clarifiers to the correct quantities. At this step in the process, the slightly treated wastewater, which is referred to as effluent, is free of solids larger than 10 micrometers and should be all organic matter, which will be treated further. The top layer of the clarified water flows over a weir wall and into the next basin in the process, called the aeration basin. Now begins the process of secondary treatment, the sole focus of which is to significantly degrade the biological content of the sewage. In many cases, this process starts with aeration basins. Effluent flows into the aeration basins, at the bottom of which are hundreds, if not thousands, of tiny air blowers that create bubbles through the water. The water is pumped into this tank along with something called return-activated sludge. You can think of return-activated sludge as a bunch of happy little bacteria that get to eat their favorite foods all day long. This introduction of significant amounts of bacteria along with the massive amounts of oxygen injected from the bubblers creates an environment perfect for the process of aerobic digestion. Summarized simply, it's the breakdown of organic matter along with the use of excess oxygen. Some older plants will add in another step before aeration basins referred to as biofilters or trickling filters. Found in many older plants, these filters essentially trickle the effluent over a medium like stone or plastic and allow for a film of bacteria to chow down on any organic matter in the water. This step is largely not used in newer plants due to more efficient and effective modern processes. But for plants with basins already installed, many still use them because they only benefit the treatment process in most cases. Following aeration basins, the effluent along with much of the sludge is pumped into a secondary filter or clarifier, where some of the sludge is removed and pumped back into the aeration basins as the return-activated sludge. Further settling of larger particles is also accomplished in these basins, as it is the final step of the process that will remove solids and larger biological matter. Water flows out of secondary clarifiers over a nearly identical weir wall to the primary clarifiers and moves on to the disinfection process. At this point, 85% of all organic matter is removed from the water, and the effluent should be safe to drink in most cases, although you probably wouldn't want to. Disinfection is the final step of the process and is usually accomplished in one of three ways, either through chlorine, ozone, or ultraviolet disinfection. Each process has its benefits and drawbacks, with each being used commonly throughout the wastewater treatment process across the world. Chlorine disinfects the water through chemical disinfection. Chlorine, which you can think of as concentrated bleach, is added to the effluent here to kill off any remaining bacteria and organisms still living in the water. When chlorine is added to kill off the bacteria, it then has to be removed before it can be discharged, as to not kill off anything in the discharge location. After this, the water is safe enough to discharge into a stream or lake. Ozone disinfection is another method of disinfection that involves pumping an electrical current through the water that causes oxygen molecules, O2, to disassociate and combine with a free oxygen molecule, forming O3, known as ozone. Ozone is an incredibly strong oxidant and causes microbes' cell walls to leak, rapid cell decomposition, and overall damage to cells. In other words, it kills off bacteria. The last common method uses ultraviolet light to scramble bacteria's DNA so that they cannot multiply. In UV disinfection, the bacteria in the water aren't killed, rather they're sterilized, rendering them harmless. If you were to ingest water with living microbes immediately following UV treatment, any harmful bacteria would be unable to multiply or render your body damage. Engineers choose between these methods based on a variety of factors such as flow rates, cost, and location of discharge, which brings us to the final step, effluent release. Effluent release exists in one of two forms. In most cases, the now treated water is released back into a stream or lake or other water source. In rare cases, usually in areas where water is scarce, the effluent discharge from a wastewater treatment plant can be discharged into another treatment plant directly, where it will be treated further for consumption. This is referred to as full-cycle water reuse. From a chemical perspective, the final drinking water is the same as normal treated water that flows through your pipes now, but due to the connotation of your drinking water being sewage just days before, this treatment process is normally shied away from or not heavily publicized. The entire process of wastewater treatment takes on average 24 to 36 hours from when a drop of water enters to when it leaves. Each wastewater plant will receive a permit for flow rates, chemical levels, and effluent quality, among other things, from the EPA that outlines the necessary treatment for a plant. Wastewater plant operators will make adjustments to a plant's operation and constantly measure levels to ensure proper discharge and proper treatment. Without these operators and the dirty job that they do around the clock, our sewage would always stay sewage, and sanitation in modern cities would be much, much worse. Wastewater treatment is an essential dirty job, and you can thank the 14,748 treatment plants in the US alone for not having to worry about what happens when you flush.
There are many forms of water contamination, for example, pesticides and fertilizers from agricultural activities. Dumping of industrial waste into seas and oceans. Oil spills and accumulation of waste, especially plastics. Wastewater from domestic and urban activities, and toxic gases from factories and vehicles in atmospheric water vapor. The main environmental problems of water are salinization of groundwater in aquifers situated close to the sea, disproportionate growth of microorganisms in lakes and lagoons due to the increase of nutrients, phosphates and nitrates runoff, eutrophication, contamination of drinking water by agricultural or industrial substances, alteration of the water cycle due to the modification of river courses, accumulation of floating solid waste in seas and oceans, and overexploitation of groundwater and surface waters. Here is some data for thinking about. 40% of the world's population is affected by water scarcity. 1.7 billion people live in river basins where water consumption exceeds replenishment. And 80% of wastewater resulting from human activity is discharged into rivers or into the sea without any treatment. Let's look at some actions to reduce negative impacts on the hydrosphere. Collection of floating rubbish, regulation of the use of pesticides and fertilizers, treatment the wastewater at sewage treatment plants, and implementation of environmental flows. What other measures are you willing to develop?